All right. So the 5.7 is enthalpies of formation. So there's obviously, as you can see, there's a lot of stuff on here. So we've got the Hess's law stuff that we've already talked about, right? Hess's law states that if a reaction is carried out in a number of steps, the delta H for the overall reaction is the sum of the delta H's for each of the individual steps. So they're just, this right here, what they're showing you is the Hess's law stuff that we've already done. All right, so I'm literally just going to skip all of this because we've already talked about all that. If a compound is formed from its constituent elements, then the enthalpy change for the reaction is called the enthalpy of formation, or delta H sub F. All right, so what this means is if you think about a, like, I can probably do it on here. So I'm trying to think of an example. Okay, so if we did this, like hydrogen gas plus oxygen, so then whatever this is, like I'm trying to think, the 2 in front of this, plus oxygen gas forms 2 H2O, 2 water molecules, or whatever, like this. Okay, the delta H of this reaction is what would be called the delta H of formation. Oh crap, hold on. Oh, okay, I'll explain in a second here. The delta H of formation for water. Now I already screwed something up. Okay, whenever you do delta H of formations, like if you look at this here, see how it's kilojoule per mole? So it's per mole of the product. So when I was balancing this, what I really should have done to be 100% accurate is I should have done this. Like that. Because I want 1 mole of water, technically. Because the water is what's being formed. So if it's balanced like this, the delta H for this reaction is the delta H of formation, the enthalpy for the formation of water. Essentially what you're looking at is all of these, the delta H of formations, all of these numbers are the energy that's either given off or absorbed when that compound is made from individual elements. So if you put these compounds together from their individual elements, that's the delta H of formation is the amount of energy that's either given off or absorbed. Okay. So, like if you look here, the AlCl3 solid is negative 705.6 kilojoules per mole. That means when aluminum chloride is made from aluminum and chlorine, solid aluminum and chlorine gas, and it's put together from that, this is the amount of energy in kilojoules per mole that's given up. That makes sense? Any questions so far on the idea? Okay, so the standard enthalpy of formation is delta HF sub F. I'm just going to highlight that so you see the variable there. And then, okay, standard state, standard conditions refer to the substance at 1 atmosphere and 25 degrees Celsius, 298 K, which is seen as like your, we didn't really deal with STP yet, did we? That's like gas laws. We'll do that next unit, I think. STP is standard temperature and pressure. This is like, these are just standard conditions. So essentially, like pressure at or around sea level, or not totally down to sea level, but near that. And then the 25 degrees Celsius is what's seen as like a typical room temperature type of thing. Okay. Those are standard conditions. So the standard state, so in other words, like what's water at standard conditions? What state of matter is it? Liquid, right. Yeah. At standard conditions, water is a liquid. If you make it hotter, obviously it turns into a gas, make it colder, it turns into a solid, whatever, but standard. So if you're looking on like the periodic table at like the elements and stuff, or some things like that, when if it's talking about something in its standard state, or you want to find a standard state, you just do whatever would be normally at room temperature and pressure. Okay. All right. Standard enthalpy. So that's the delta H prime. Okay. Standard enthalpy, delta H with the little prime circle, looks like a degree symbol, is the enthalpy measured when everything is in its standard state. Okay. So standard enthalpy of formation of a compound is the enthalpy change for the formation of 1 mole of a compound with all the substances in their standard state. So basically, the green highlighted one is a combination of the yellow and the pink, putting these two ideas together. The enthalpy of formation and the standard enthalpy, you're putting them together, and it's standard enthalpy of formation. It's the enthalpy of formation when everything is in its standard state. Okay? Does that make sense? I know it's terminology is new, and so it can be a little confusing, but all right, questions so far? So all of the delta H prime of F, the standard enthalpy of formation for the compounds, are in Appendix C, the one that I gave you guys. Okay. All right. A large majority of the values are negative, meaning that most formation reactions are exothermic. Anybody know why that is? When a compound is formed, it's giving off energy. It's exothermic most of the time, not always. Okay.
Because the chemical bonds are becoming more stable.
Yeah, good. So what happens is when it bonds together, those atoms in that, the reason it's doing that, it's combining, is because it's more stable together as a compound. And the more stable something is, then the less energy it needs to stay in that situation or that state. So take like hydrogen and oxygen. Hydrogen and oxygen are pretty reactive substances. Okay. We know that hydrogen combusts very easily. We know that oxygen oxidizes many different things. So when they come together and form water, yes, water is still reactive, but it's not as reactive as these two are separately. So it actually gives off energy because it needs less energy. It's more stable. It doesn't need as much energy to exist as water molecule versus the individual element molecules. Okay, good. If there is more than one state for a substance under standard conditions, the more stable one is used. For example, When dealing with carbon, we use graphite because graphite is more stable than diamond or C60, which is a buckyball. This is super important. I've already highlighted a lot. I'll mark it with red. The standard enthalpy of formation of the most stable form of an element is 0. Of an element. Okay? Standard enthalpy of formation of the most stable form of an element is 0. Because it wouldn't take any energy to form it. It is what it is. So like if you look on your list, they're listed on here. You should just know that they're 0, but they're listed on here as well. Like look at the very first one, aluminum. 0. Aluminum as a solid, 0. That's the most, it's just itself. It's aluminum. Like it doesn't take any energy to make aluminum from itself. Like it is already what it is. Okay. Now you can look at some other ones like here, let's see. Well, here's the carbon ones it was talking about. So you've got carbon as solid, but graphite is 0. And then carbon solid as diamond is 1.88. So you can see they're almost exactly the same, but not quite. Like really close.
Pressure change?
Okay. Yeah, it has to do with the it has to do I honestly don't know exactly what it is, but I know it has to do with the arrangement of the arrangement of the atoms and the like different forces that hold them together, like the London factors and the hydrogen bonds, all that kind of stuff. Um, and then I don't even know what the heck carbon as a gas is, but apparently it's possible. I don't know what it would be, but carbon as a gas, and see there, that's not the most stable form. So, and then other stuff that you're probably familiar with as well. Like if we look at, okay, first of all, I guess I should mention this. If you notice, these are in alphabetical order by the element name. Okay, so that's kind of how you look to find stuff on here. And there's two columns. Okay, so but if you're looking for like, it depends on what you're looking for. So for example, if you're looking for carbon dioxide, that's going to be under carbon. Here, like carbon starts here, and then carbon dioxide over here. Okay, but there are like, so if you look at oxygen, so water is actually under oxygen. So if you look, see here on the second page, oxygen, water is actually under oxygen there. I don't know how it determines where it's under. Most of them are under the first thing, but water is under oxygen instead of under hydrogen. I don't know why, but if you look at the water, see how it's gas and liquid, there's more than one. So be careful when you're looking up the numbers. Make sure you've got it in the right state of matter. You're using the right number for the right state of matter. We've got monatomic oxygen as a gas, not as stable as diatomic oxygen because it's part of Hofbrinkel, right? When it's alone. So O2. So all of your Hofbrinkel, their standard state is going to be diatomic. Is going to be the one that's got a 0 on it. Anybody know what O3 is?
Ozone?
Yeah, good. Ozone. So you can see that's not as stable either. It's got a enthalpy of formation compared to oxygen, diatomic oxygen. Okay. So this, by the way, I think I told you guys this already, but just in case, this hydrogen peroxide H2O2, that's an L. There was a misprint in the book, so I corrected it just so you know that's an L though if you're looking at it. Okay. All right. How do we use the enthalpies of formation to calculate enthalpies of a reaction? So we use Hess's law, So we start with the reactants, decompose them into elements, then rearrange the elements to form products. The overall enthalpy change, blah, 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 blah. Okay. So essentially, what you do is the delta H prime of the reaction is equal to the delta H prime of formation, delta H of formation of the products minus the delta H prime formation of the reactants. Okay? And because of this, you do not change signs for the reactants. All right. Now, what do I mean by that? Well, your book does this thing, and I think it unnecessarily complicates it. Your book does this thing where it does this. It breaks them all down, and then it calculates. I guess I shouldn't point up there because people can't see it. It breaks them down individually. So it'll take everything in it'll take everything in here, and it'll break them all down and figure out the delta H of formation for each thing, and then add them all together. But if you do that, you have to change the sign of the reactants. I think that makes it more complicated. I just tell people do this. Add up the delta H of formation of the products, find it for all the products, add it all together, find it for all the reactants, add it all together, take your products minus your reactants. Then you don't have to worry about flipping signs or doing anything else. Okay? So, how do you do that? Well, that's this here, this thing. Okay? Where the N and M are the stoichiometric coefficients. Okay? So, stoichiometric coefficients so it's that times the delta H of formation. Okay, now, I know it's still not probably real clear. That's why I have some examples. Oh, we're doing okay time-wise. Okay, so let me see. I have that. All right, I'll show you this. I'll put this up. I'll put this up with the notes that I have done. I'll make it part of the copy. But I don't want everybody to take time to do it right now. I just want to show you, and then we'll do some of the problems. So this equation, right? Where is it? Here. This one. The C3 gas plus 5O2 gas yields 3 CO2 gas plus 4 H2O liquid. Okay. To find the delta H of the reaction, we're taking the delta H formation of the products minus the delta H formation of the reactants, right? So look what I have here. Zoom out. Oh, no, actually, it's pretty good. Okay. So look what I have here. So the reactants The reactants are these, right? C3H8 gas and the 5O2 gas. Okay, so all I did was you go to this, thermodynamic quantities, and I looked each one up. So, and I'm splitting these up. So C3H8 gas. So I go on here, C3H8 is probably under carbon. C3H8 gas is right here. It's negative 103.85. You see that? Okay, 103.85. So the delta H of formation is 103.85. I take that times the coefficient in front of that in the equation. So there's nothing in front of it, so it's a 1. So times 1. I get this. I do the same thing for oxygen. O2 gas, okay, you should know that that's the standard state of the element, so it's a 0. But if you didn't, you can look it up. 0 for the enthalpy of formation. So that's here, times the coefficient, 5. 0 times 5 is 0. Add them together. Okay, I do the same thing for the reactants. The two reactants, I find the delta H of formation for each one. I multiply it times the coefficient. Get those numbers, add them together. Okay, then all I did, so this is the delta H of formation for the products. This is the delta H of formation for the reactants. I take products minus the reactants. You got to be careful here. My reactants are a negative, right? So it's minus a negative. And we add them, we get the delta H formation for the whole reaction. Okay, does that make sense, at least looking at it? Questions so far? Okay, now let's actually walk through one. I think it'll be even easier to understand when we do that. So let's start with the enthalpy of formation, sample exercise 5.11, 5.11. This one? Okay. Calculate the standard enthalpy change for the combustion of 1 mole of benzene, C6H6 liquid, to form CO2 and H2O. All right, to do the standard enthalpy change for this, we've got to make the balanced chemical equation. Okay, so it's combustion. So we've got C6H6 liquid plus O2, and I'm leaving space for balancing, gas, because it's combustion, yields CO2 gas and H2O liquid. All right. And we're looking, we don't know what the delta H of the reaction, right? That's what we're trying to find out. Okay, balancing. Okay, so the balancing would be, don't write this in. I'm going to show you first. It would be 2, 15, 12, and 6. Okay, but what are we trying to find it for? 1 mole of benzene, right? In front of this, we've got 2 moles of benzene. We need this at a 1. So we're going to go through and divide everything by 2. So this becomes a 1. This becomes 15 halves. This becomes 6. And this becomes 3. All right, everybody okay and with me so far? Questions? Okay, so we got the balanced equation. Now, what we're doing is this. We want to find the delta H of the reaction, which means we're going to take the delta H of formation of the products minus the delta H formation of the reactants. Okay. Now, we don't have to do it out like we did this one, like that. I mean, you can if you want, but you can actually do this just sort of horizontally, like this. Delta H of reaction equals. Okay, now I'm gonna put brackets to kind of keep myself organized here. So like this, and I'm gonna do my delta H of formation for my products. Okay, so remember, it's coefficient times the delta H of formation. So what's my coefficient for my product, my first product for CO2? No, product 6. There you go. So we got 6 times, now I'm going to look up CO2 gas on my sheet, my packet sheet thing. So CO2 should be under carbon. Yep, there it is. CO2 gas, negative 393.5. So I put that in, negative 393.5. And really watch your signs, guys. That's what trips people up more than anything, to be honest. Okay, now, so I've got that. That's for the CO2. Now, plus 3 times water liquid, which you're going to look up on the sheet, is going to be negative 285.83. Right? And then that's all my products, right? So I'm going to end bracket it. And then I'm going to go minus. Now I'm going to do that for my reactants. So another bracket. My reactants here is just a 1. And I look up my delta H of formation for C6H6 liquid. It's 49. Plus, now I'm going to put all this in so people can see where I'm getting the numbers from. But like in this reality, you don't even have to put this in there because, so it'd be 15 halves, right? But the delta H of formation of oxygen, because it's the element in its standard state, would be what? 0. Anything times 0 is just 0. So in reality, you could have just stopped after the 1 times 49. Now, all you do is the math. Add all this up, then subtract them. And so I'll show you the in-between step. Just, you don't have to write this down. I'm just doing it so people have it in case they want to know if they aren't getting the same number. So this is 3,218.49 minus 49, which gives us delta H of reaction of negative 3,267.49 kilojoules. Okay. I'm not worried about significant figures with these. Just do whatever it kicks you out, and I just leave it at that for what we're doing. All right, does that make sense? People feel comfortable so far? All right, let's look at B. Compare the quantity of heat produced by the combustion of 1 gram of propane to that produced by 1 gram benzene. Okay, so the first thing is we have, wait a minute. Where did I get that? Did I miss something in the book? I might not have picked something in on accident. Let me see. Page 192. 192. Oh, wait a minute. Oh yeah, they're using sorry, I didn't realize this. They in the actual text of the textbook, they found okay, sorry guys. Luckily I have it in my notes here, so in the actual text, they gave you this, so I should have added this to it. Um they they did the work to figure out the delta H prime of the reaction for propane is negative 2,220 kilojoules per mole of propane, which is C3H8 gas. Okay. So you would need that information like to in order to do this. Okay, so we need that, and then we need this up here that we have. So let's look at propane. So propane is negative 2,220 kilojoules per mole, right? And the what was the other one? Benzene is this one up here, negative 3,267.49 kilojoules per mole. Okay. So I got this one from part A, right? Okay. Now this is saying the combustion of 1 gram of propane compared to 1 gram of benzene, right? So right now we're comparing moles of each. So we want to do grams. So all we have to do is convert from moles, so moles on the bottom, so moles on the top, to grams. Okay, this is the C3H8. So it's 1 mole and it's 44 grams. That comes from the molar mass of this, right? The C3H8. And then we're going to convert moles to grams of C6H6, right? Is that, yeah, C6H6. Okay, so we convert these from kilojoules per mole to kilojoules per gram. So this first one comes out to be negative 50.5 kilojoules per gram of C3H8. And this one comes out to be negative 41.9 kilojoules per gram C6H6. So if you're comparing them, you could say something like 1 gram of propane produces about 9 kilojoules more energy than benzene. When combusted. Okay. Make sense? Questions on that? All right. Next one. Sample exercise 12. So the standard enthalpy change for the reaction, they give us the reaction, is this. Okay. So that's the delta H of the reaction is 178.1 kilojoules. From the values for the standard enthalpies of formation of CaO solid and CO2 gas given in Appendix C, calculate the standard enthalpy of formation for CaCO3. So it's still using this. I don't know if I'll have time to go through all this, but I can get you started on it. Still using delta H of the reaction equals delta H formation of the products minus delta H formation of the reactants. Okay? But it's asking for something different. What do we have? Well, we've got the delta H of formation of this, right? So we've got this part over here. That's 178.1 kilojoules. Delta H of formation of the products, that's these things. That's what they tell us to look up. So, we got a bracket. The prefixes are, or the, I'm sorry, not the coefficients are 1, right? So, CaO solid is, wait, CaO is calcium, so it'll be under calcium. CaO solid is negative, wait, where'd that go? 635.5. Okay, plus CO2 gas. CO2 gas is negative 393.5. Everybody okay with where I'm getting the numbers from so far? Okay, then minus the delta H of formation of the reactants. Well, we only have one reactant, right? But guess what? That's what we're looking for. So we got 1 times x, like that. All you're going to do is solve this equation for x. And that's your delta H of formation. What you're looking for is the delta H of formation of CaCO3. So if you solve for x, that's the delta H of formation for that. I'll finish this up and this will go on online as well. Okay? Questions? All right, I know there's a lot to it. Let me stop this real quick.